So while I'm doing this, pull up your chapter 14 review. So it was the extra PDF that I gave you guys at the very end after we did 14 to just kind of catch us up and put us all back in the same. So we're going to do some problems on there that we hadn't finished. Use password. Go, go, go. So freaking tedious. Has anybody else noticed that? Like maybe you guys just never go to Pearson directly, but I used to always go like mlm.pearson.com and then it stopped letting me in and I don't know why. I have to go through Blackboard. It's very irritating. All right, 16 dynamic study module, student view. Okay, so let's see if I can. Oh my gosh, didn't you just say H2S?
Yes.
It was literally the first one. Okay. All right, I'm not going to read through all of that stuff. It does say when you're allowed to use an approximation or not. I guarantee you, 10 to the negative 7th, you're totally going to be able to use an approximation. No question there. Okay? So let me just screenshot this so I can write on it. Okay, so let's rewrite this over here, 2H2S, and it's initially that, and there's no other stuff in there. So we are reacting it to form the H2 and the S2, so 0.1 molar, none of this to start. So we do minus 2x here, plus 2x there, plus x there. And this is where the approximation is going to allow us to drop that minus 2x. Okay? So our k should be equal to 2x squared. So Faith, look at your notes while we're doing this too. Over x equals 0.1. And we're not including that minus 2x. Let me change this color so it's a little easier to see. Okay. In fact, if you tried to do this, you would end up with a quadratic or a cubic formula. You'd have x cubed, which we will have x cubed, but then we could just do a cubed root. So it's not cubic in the sense of like x cubed, x squared, etc. So then on this one, this is equal to 1.67 times 10 to the negative 7th. Yet 4 and 5 are kind of borderline. By the time you get to 6 and 7, like there shouldn't be any issue. So 1.67 times 10 to the negative 7th times 0.1. Now this is going to be on top. This is equal to 4x cubed. So I'm taking k, I'm multiplying it by 0.1, so multiplying both sides by 0.1 to get rid of it, and then I'm dividing both sides by 4 to get rid of that. So I get that x cubed is equal to 4.175 times 10 to the negative 9th. So I need to do a cubed root of that. And that comes out to be 0.0016, which is 1, 2, 3. So 1.6 times 10 to the negative 3rd. Now they have 1.49 is the closest one. Let's make sure that that's there. Oh, wait, sorry. We probably did something wrong. Equilibrium concentration. Oh, no, we didn't. Equilibrium concentration of S2 is just X, so it's not 2X or anything. So that should be correct. Let's go back to the... what the heck am I supposed to do? Am I supposed to click it again? Yeah. Okay. You were sure and incorrect. Okay. Yeah. No, because when you solve for X, now you go back to these equilibrium concentrations and plug X in there. So S2 would be equal to X. It is asking about S2, right? Yeah, equilibrium concentration of S2. Oh, the point 1. You're right. You're right. All right, let's look at this and make sure there isn't any other issues. 2x squared, x 0.1. I hope that's the only issue. 1.67 times 10 to the negative 7th times 0.1 squared divided by 4. Oh, hang on. Times 10 to the negative 7th. Okay. Times 0.1 squared. Should just change it by exponent. Yeah, so this should be to the 10th. So if we do that cubed root, that should still come out to 4.175 times 10 to the negative 10th. Oh, okay. Yeah. So 1, 2, 3. It was just this issue there on the bottom. So this is correct. 4.74 times 10 to the negative 4th. So, I mean, I guess it's possible, Faith, that it was like always a little something like that. The other thing you can do is you can always take your X. I kind of forgot about this. Again, a child reminding me. You can always go back and check your answers, right? So you can plug into your X and then see, does it still equal 1.67 times 10 to the negative 7th? And this may be a good reminder of not being lazy about like not writing out the K expression. Because I think if I had gone through and done H2 squared S2 over H2S squared and then plugged the numbers in, I think I would be less likely to have forgotten that square there rather than me just like speeding through it. So that may be a good reason for you guys to do that even on an exam. And when I'm writing like an exam key or like double checking the exam to make sure like all the right answers are there and stuff, I will be way more thorough in my work. Like I will show the work for like a molarity calculation or something just so I don't miss stuff like that. So it is a good rule of thumb. I don't know if that was the issue last night, but yeah, sorry. Okay. Do you guys want, so the stuff I have for 14 is mainly like Henry's Law that we kind of breezed over because I said it's so easy. And then people were like, it's not that easy. So there was that. There was one of a little bit more complicated, like freezing point depression. And then there was one more that was a little bit more complicated, osmotic pressure. So those are kind of the 3 for 14 that I picked out. What other ones?
I have number 19
on the practice exam. Okay, I gotta blank this because sometimes it like inadvertently shows grades when I go to Pearson. Chapter 16 practice exam or 14? 14, okay. There we go. And then what number did you say?
19.
Okay, is it 14.59, exercise 14?
Yeah.
Okay. I can never remember if I, yeah. Okay. That's okay. It's good review. Okay, so this is a dilution but it is also involving an initial concentration. Let me put this in a file thing. Wait, that just saved the blank screen. Nice. One more time. Oh, it says it's saving 2 items. Well, should be in there then. Sorry, it's so tedious sometimes. Okay. So this is a dilution equation, but it's incorporating a percent by mass in addition. Okay, so we've got 70.3 HNO3 by mass. So every time you have a concentration unit that you're not super comfortable with, like molarity, let's go ahead and define that. So 70.3% means, and it's by mass, means 70.3 grams HNO3 over 100 grams of the whole solution. We probably don't need to know it broken down into water, so I'm not going to mess with that. I'm just going to leave it as grams of solution. Realize if for some reason you needed to know how much water there was in particular, it's going to be that 70.3 plus whatever else makes 100. So 29.7 in this instance. So you can break it down further if you need to. One note, we were doing like a part per million, part per billion question, one of those in my other class. Sometimes on the denominator, like if you have 1 billion grams and like, I think it was 15 grams of the solute, you can basically assume that that billion is just the solvent. Because if you were to try to separate those, it would be like, 15 grams of the solute and then 9985 grams of the solvent. So you can kind of approximate it if they are very, very large numbers on the bottom. Side note. Okay, has mass and it gives us our density. So that's how we're going to get this converted into molarity. Okay, so how much concentrated solution would it take to prepare 1 liter of 0.1 molar HNO3 by mixing it with water? So here we can get to the moles that we need. So we're going to take this value and convert it to moles. And then we're going to use this to use that number of moles to convert to how much, so probably liters or milliliters. Okay, this is the same as the dilution equation. It's just stepping through the process is a little bit more complicated. So another way that you could do it is you could actually convert the percent by mass into molarity, and then you could do M1 V1 equals M2 V2. I wouldn't necessarily recommend that because I think it's probably more work, like more steps that you have to go through. You do have all the information to do that though. So you could convert the HNO3 to moles. You use the density to convert the grams into liters, and then you can do molarity and plug it in here. So is that less work? I don't know. I feel like that probably would make you guys more comfortable, but any votes on who, if you care which way we do it? All right, I'll do it my way because then you can see what I would say is more unusual or harder method that might apply to other things. Okay, so we need to first figure out the moles in the thing that we're trying to make. So 1 liter times 0.110 moles per 1 liter means we have to have 0.110 moles of the substance. So we need to figure out how much of that nitric acid solution do we need. So we're going to use that as a conversion factor. And we're going to say 0.110 moles nitric acid. But we can't go to moles directly to use the percent mass nitric acid because that's in terms of grams, okay? So I'm going to have to actually go from moles out to grams to use that, which is a little bit unusual. So I do need the molar mass of nitric acid. Which is 63.01. And you would have had to use that if you'd gone to molarity as well. And now, so this is grams of HNO3. Now I'm going to use this percent as a conversion factor. So I'm going to put 70.3 grams of nitric acid on the bottom, the 100 grams of solution on the top, but it wants volume. It says how much. Oh no, the answer down there says volume, molarity. Mils, rather, okay? And move this over one more so that we can do the density conversion, which was 1.41 grams per 1 milliliter. Okay, so recapping. We found the number of moles that we needed. They made it nice and easy for us to make this solution. We took that number of moles, converted it to grams, so that we could use the percent by mass conversion, okay? So 70.3% means 70.3 grams per 100 grams. Then we use the density to get that into milliliters. And I don't know if we actually care about the answer at this point or if we just care about the work, but I will plug it in just for the sake of doing it. 6.99 mils. I don't know if this is one of those that changes the numbers in the question. I guess if not, then you guys have the answer for this one at least, the correct answer. Yep. So what that means is that if I use 6.99 mils of the concentrated solution, fill it up so that there's a total of 1,000 mils, 1 liter, it will result in a solution that's 0.11 molar HNO3. Yeah. Why does that keep happening? It's really embarrassing. With this calculation, say that one more time, louder. You're retyping it in and like this work and you just got a different answer? Oh, okay. Try that. It's bad when your professor can't type in a calculator. 20.3. Yep. Yeah. In the percent solution. Yes. Yeah. Yeah. And that's like a third way that you could do it. The second way too was like converting to molarity and using the dilution equation. So honestly, any of those are fine as long as you are canceling out your units and getting to the correct thing. Okay, let's flip over to 14 just because I don't want to neglect it. It was older. And I do worry about us forgetting what was on there. I'm going to have to erase some of this because I only have one. Okay, don't look. No hints. Okay, so I'll tell you, there's one Henry's Law. Let's just show you the work for it and then do the more complicated one. Because I don't want to waste the time by doing like 2 of them. But at the same time, I don't want to throw you a difficult problem when you haven't seen an easier problem. Although maybe you saw it, No, you haven't seen it recently because that homework was due a while ago. Okay, so Henry's law, the equation's wasn't on your exam equation sheet. It is on the exam now, though. So the solubility equals the pressure of the gas times the Henry's law constant. That is literally it. If they give it to you in the correct units, and maybe in the next one I'll just put it in the correct units, so they give you atmospheres. So literally all you have to do is 1.5 times that constant, 3.76 times 10 to the negative fourth. And what that's telling you is the molarity of, in this case, helium that can be dissolved into water if you put a pressure above it of 1.5. So molarity, moles per liter. It's no different than like dissolving a salt in water. It's just that you're pushing that gas in by applying a pressure above the liquid. Okay, so the next question is going to take this one step further and utilize that molarity. So if you have these notes out, these are the file that was on Blackboard that I just kind of added on for a 14 review. So if you want to pull those open, if you don't have them, you can get them on Blackboard. Okay, so go ahead and take a look at this problem. What mass of oxygen gas dissolves in water? So, okay, first kind of red flag, it's asking for grams mass. So that's going to be a little bit different. I'll go ahead and just convert the pressure for you, which is 0.993 atmospheres. Okay. So what I would say is like start with what you know. Start with the Henry's law equation. You know you're going to use that because they give you a constant, right? And then see where that can lead you to help you figure out a number of grams. Okay, so if you've gotten there, check the solubility, which is equivalent to molarity, how much moles of oxygen you can dissolve per liter. And then they're asking for the number of grams of that oxygen in 600 mils. So this is no different than if you had a solid dissolved in water. You convert the milliliters so that you can use the molarity as a conversion factor to get moles. Then you do a simple gram to mole conversion. So 600 mils to liters. And then using that molarity, and the molar mass of oxygen. Remember, oxygen gas is 32, it's O2. I'm gonna have to have somebody checking my math all the time. Oh, well, I guess the right answer is there. It's probably right. They really should have done one that's half of that, because a common mistake I can see here is someone looks up oxygen and just puts 16, but it's oxygen gas, O2, so. So on the exam, this one's probably a little bit easy to just do this part. Maybe I would like simplify it a little bit by like saying, I don't know, how many moles do you need? Or like I'd say oxygen has a molar mass of 32, just to like remind you so you don't make a mistake there. I definitely would convert it. Like when I go and I just did this morning, I finished it, was like, worked through the test, and then I guess it was yesterday, simplified some of the things like, oh, I'm going to convert this part for them, or just so that it's focusing you in on the actual problem, not like you're not going to get stuck on the millimeters of mercury or something like that. So this whole thing is, if you can do this comfortably, you're probably going to be fine on a problem, you know, on Henry's Law on the exam. Okay, let's do, I want to do an osmotic pressure, but I also want to do a freezing point depression. 10 minutes. Do we need to have a vote? I'm kind of leaning towards this one. Okay, this is another good one that's like a step above just a straightforward osmotic pressure calculation. So it is, you have to utilize the osmotic pressure equation, and then you have to take it one step further. Okay. Just as a quick recap in case we don't have time, on I, I'm going to use some of these salts here as an example. I'm just going to rewrite what I'm doing here. Please remember that in the freezing point depression and boiling point elevation, that is giving you, you have to account for how many things your molecule breaks into once it gets into water. So a covalent compound like this will just break into a molecule. It's not gonna break down any further. So there's only one thing for every one thing you put in. NaCl though, it's one thing when you start and you put it in water and it breaks into two things, into ions. So for a covalent compound, it's always one. For an ionic compound, it's how many ions there are. So NaCl is 2, whereas CrCl2 would be 3. Because when you put 1 unit of SrCl2 into water, it breaks apart into SrCl- and Cl-. Okay? What this really means is that the more an ionic compound is way more effective at the same concentration, it's way more effective at reducing the freezing point or elevating the boiling point. That's another good point. You need to know that freezing point always decreases and boiling point always increases when you add a solute. Because those equations only tell you the change in temperature. Like this problem, we didn't do it, I did in my other class, but it says 102.5. Like you needed to know that that difference goes up for boiling, but then when you do the freezing one, you need to know it goes down. So it should be a negative number in the case of water. Okay, because the equation doesn't account for that. The I thing is incorporated into osmotic pressure as well. And in this instance, it's a protein, which is a covalent compound, so I is just equal to 1. Okay, so starting with the osmotic pressure equation, just kind of plug in and see what do I have and what could I solve for, and then see how you can use that to take it the step further that it's asking, which is determining molar mass of the protein. Like when you see that, you're like, well, what's the chemical formula? Do I need to add it up on the periodic table? No, you don't know what it is. They're trying to get you to use the information you have. So start with this equation and see what you do have to get to that point. Okay, so if you need some hints or want to check your first part of the calculation, that's up there. So from the information you're given, you can calculate the molarity. You have the osmotic pressure already. That does need to be in atmospheres. And temperature needs to be in Kelvin, and the R is a constant. So you calculate the molarity, but the question is asking for molar mass. And there's also a lot of other information in that blue block. So the best way that I think you can think about this is the units of molar mass, which, it's multiple choice, it's right there. So think about what are the grams and what are the moles, and then divide one by the other. So the grams is actually given to you in the question. I have to put it in grams instead of milligrams, but it's pretty much given to you. And then the moles, it tells you it's a 50 milliliter solution. Well, if you know the molarity and you know the volume, you know the number of moles then. You just have to plug it in. Okay, and then that will go on the bottom, and then you divide one by the other. I've got to figure out how to force my calculator to put this in scientific notation. 1, 2, 3, 4, 5, 6. Okay. It's not right. Let me double check a couple things. 2.81, 60. Divided by 0.821, 298. That is correct. Moles per liter. 50. Oh, I think I just forgot a parenthesis. 0.0256 divided by parentheses 7.5 times 10 to the negative 6th. Great. Okay, so this comes out to 3,000. I think I rounded a little bit too quickly, but I have 3,413. That 7.5 was probably rounded too much, maybe the 1.5. This is not crazy. Proteins are really, really big molecules, and so they have really big molar masses. So that is your answer for the molar mass. So again, don't let the multi-part questions freak you out. Let them be a guide of like, this is the hardest you would see. If you can feel comfortable with this, certainly you can do a plain osmotic pressure calculation, right? Okay, practice exams, final attempts due tomorrow night, and then exam on Friday.
How long will you be in 305, you said?
Yeah, I'll be in there right now, and then I know there's people coming at 1, so